Hello all. Welcome to this new episode of QWave. Today we will have Sofia Vallecorsa, and CERN talking about the CERN Quantum Technology Initiative and advancing the quantum research. So we will hear about the CERN Quantum Technology Initiative, a pioneering effort exploring how quantum technologies can support high energy physics research and how the CERN is actually making this on their own expertise, contributing to this quantum revolution. Also, we'll hear about the hybrid quantum computing and quantum networks and all of the things that CERN is doing. But before jumping in, I want to introduce Quick for those who don't really know what is Quick and just came across this video and the many other videos that we have within the QWave webinar series. So Quick is a non-profit association established back in 2021, and the main mission is to grow and strengthen the quantum technology industry and position Europe as a global leader of the sector. A big showcase about the industry. So we are so Quick is the European Quantum Industry Consortium, and we want to push the industry. Given that said, I also want to introduce the QVC Summit that this year will be at CERN in Geneva, and it's going to be on the November 26th and 27th, the QVC Summit, and also we will have some activities on November 25th, sorry, at CERN. So once I have introduced Quick and talk about the QVC Summit, that if you want to know more, you can contact Quick or contact me, or just send a mail. I will introduce our speaker for today. That is going to be Sofia. Sofia, that let me get her in. So she's a researcher at CERN with expertise in scientific computing, machine learning, and quantum computing applied to high energy physics. She holds a PhD in physics and currently leads the CERN Quantum Technology Initiative, coordinating teams investigating the potential of quantum technologies in the context of CERN's mission. Sofia also heads the computing and data science section in CERN's IT department, driving cutting-edge research at the intersection of AI and quantum computing. Wow, so really, really cool, I guess.
Baby. Thanks.
So let me get here the presentation, and Sofia, the floor is yours.
So thanks again for the invitation and the nice introduction. First, I'm very happy to be here. We are glad and to host the summit in November. So let me tell you, in preparation of all of that, what is it that we do at CERN with respect to quantum technology? But before going into that, I already wanted to give you, the conclusion of my talk. I'll start by describing you the lessons learned we have gathered through the first years of our initiative. And there's only three of them. They're very important, I would say, but also simple to understand. The first one, and most important probably, is the fact that we do understand that quantum technologies can have a transformative impact. This is true in many domains, but in particular for high energy physics. However, in order to achieve results and impact, it is important to study those within realistic settings. This is really at the core of what we do for the Quantum Technology Initiative, as I will show you. The second important point we learned is that there are a lot of technologies that we are developing and that are key, essential to the development and research that we do for physics, high energy physics in particular, and many of those can actually be also applied and optimized for other domains, and notably quantum technologies. And so I will also give you an example of this. And the third point is about collaboration. As researchers, as scientists, we know that collaboration is key for advancement. This is even more important in the field of quantum technologies. The ecosystem is very broad and varied, and the technologies evolve very rapidly. And I think that as a community, we can leverage and we can contribute to it only if we take a collaborative and open research approach. So, few words about CERN. Some of you will know us already. CERN is the world's largest laboratory for particle physics. The infrastructure is sitting at the border between Switzerland and France, close to Geneva. This is a very nice picture that highlights the and traces the Large Hadron Collider. In the area, you can see the Lake Geneva and the Mont Blanc in the background. The goal of this kind of research is really to understand the fundamentals of particles and the laws that describe matter and the universe, the behavior of the universe. And in order to do so, the most important facilities that we have at CERN is at the moment the Large Hadron Collider. So you could see a little bit of it as traced in the previous slide. Let me give you just.
I think that we lost you for a minute or half a minute.
Yes, I was going to say, I just saw a message. Shall I start again?
Yeah, please.
From
this slide, yeah.
From this slide, okay.
Yeah.
So I was describing the Large Hadron Collider as the biggest experimental facilities we have at the moment. It accelerates particles close to the speed of light over a ring that has a 27-kilometer circumference and is about 100 meters underground. But the accelerator is not the only big infrastructure. It is paired to a set of detectors that are actually measuring the results of the collisions. The Large Hadron Collider produces more than 1 billion particle collisions per second. You can imagine how difficult it is to actually describe and reconstruct all of the specific physics information out of such amount of data. The way we can study the physics processes that were at the origin of this collisions is by studying the new particles that are created while they travel through the detectors. And you can think about the detector as these huge three-dimensional cameras that are able to take very, very big, high-resolution pictures at a very high rate. Okay, we're talking about 40 million pictures per second as an order of magnitude. Now, the data that is produced in this context is huge. It requires also very large and complex computing infrastructure in order to process it properly and extract most of the information out of it. And the WSCG, so the Worldwide LHC Computing Grid, is the distributed infrastructure that the community has been using for many years for analyzing the data that is produced by our experiments. You can see some numbers about the computing grid here in this slide. We're talking about 1.4 million processing cores. Those are mostly CPU-based. This is mostly CPU-based infrastructure. They are scattered across 170 data centers all over the world. And currently, the data, actually the numbers I got even higher than what you see here, but let me say that at this stage, we have more of the order of 1,500 petabytes of CERN data that is stored worldwide. The next step is to upgrade to the high luminosity Large Hadron Collider. This is happening. The idea is that this enhanced accelerators with the enhanced detectors that will collect the data will be able to study 10 times more collisions that we study today. And so you can imagine that together with the increase and the more complex challenges that we'll have to face, we will also need improved computing infrastructure in order to match. And we expect starting operations of the high luminosity Large Hadron Colliders in the middle 2030. What does it mean from the point of view? I mentioned challenges. I mentioned we need computing, different new computing infrastructure. What does it mean? If we think of analyzing the data that is produced by an accelerator like the high luminosity Large Hadron Collider, we will need to be able to describe, disentangle, characterize all of the particles that are produced by the collisions. And in this little representation that you see here, you have a glimpse of what, in terms of scale and complexity, I'm talking about. Each one of these purple lines is actually representing one particle that is created out of a collision. And you can imagine that there will be order of 200 collisions that happen simultaneously. So this gives you an idea of what the challenge would be in terms of data representation and processing. And this is a evaluation on how we expect the evolution of the computing technology to match the needs of the community once the high luminosity LHC will start running. And what these plots tell you is that unless we focus on R&D, so we study new approaches, new technologies for processing our data, we will not be able to rely on the current infrastructure. And so this has sparked since many years, I would say rather sustained R&D set of R&D activities that happen at different level, at the level of the technological infrastructure, but also software and approaches to finding new strategies to data processing, for example, artificial intelligence. And you can probably imagine where I'm going with all of this. Quantum computing is also one of the technologies that we are investigating because of this sort of challenges that we know will have to face. So let me go to the topic of this talk, which is the Quantum Technology Initiative at CERN. Now, the technology initiative was launched a few years ago in 2020. This was really an exploratory initiative that was intended to understand what is it that quantum technologies could contribute to our research, and the challenges that I described to you, but also on the other, let's say in the other direction, what are the technologies and the innovations that we do because of high energy physics that could be reused in other fields. And the Quantum Technology Initiative at CERN is organized in 4 main areas. 3 of them are focused on 3 different scientific or technological areas that we all can identify that are the computing and algorithms are areas, the networks and communications area, and then the sensing part, the quantum sensing part. We also have a dedicated focus group on collaborations for impact. As I said at the beginning, this is very, very important, and it really drives most of the work that we do. And again, let me stress, the initiative is really about this double direction. There is this interchange that happens between the work that we do at CERN and the development of quantum technologies in the broader context. So let me give you a few examples of how do we see quantum technologies contributing to research in high energy physics at CERN. And I will focus on the aspects of hybrid quantum computing. And I stress the word hybrid here. This is very, very important for us at this stage. It is clear that the trend is to see quantum computers integrated in broader classical infrastructure. This is something that in the community is not new, I believe. It is also true for the high energy physics computing model that, as I said before, is evolving, needs to evolve to meet the future challenges. And so the way the Quantum Technology Initiative contributes to this is by studying and developing quantum algorithms, and in particular, quantum machine learning algorithms that are suitable to run in hybrid settings. We want to understand the performance of near-term quantum hardware embedded in broader, in hybrid setups, so in broader classical setups. For example, studying the integration between HPC and quantum computing, but also obviously, because I will get back to this at the end of my talk, but because timescales are actually, for high energy physics experiments are actually very long, we are also interested in studying scaling towards fault tolerance and what the, having an idea of what the performance and the reach of this technology will be in that setting, okay? I still want to stress that most of the developments that I'm just listing here are actually common to many, many areas beyond high energy physics. So for our domain, we have highlighted a range of algorithms that are developed either as hybrid algorithms suitable to run on near-term devices, or algorithms that are better suited to run in fault-tolerant settings, or further down the line of development, let's say. So this was actually a community exercise that brought together initially researchers from CERN, from DAISY, and from IBM. We set up a working group that was really focused on studying quantum computing for high energy physics, and we made the effort of highlighting what kind of problems in either the theory domain or the data processing, experimental data processing domain could be mapped to quantum algorithms. And the sketch that you see here gives you a summary of what we have, of our findings. And all of the details, I mean, if you are really interested in the different problems that are typical of our data processing chains, or that our theory colleagues face when they need to simulate specific phenomena, all of the information is available in this publication. But I wanted to stress a few points because I think they're important for the discussion about quantum computing in general, and it's the discussion about what useful actually means in this context. I said at the beginning, we are interested in in understanding the scope or the performance of quantum computers in realistic settings. So you see here a few examples of what we look for when we study quantum computers for high energy physics. So first of all, we redefine the concept of quantum advantage towards something that is, I would say, more flexible. We want to prove usability of these kind of algorithms on problems that are typical of our state of the art. And so you see here 3 examples of what this advantage, or let's say usability, could mean. On the far left of my slide, you would see this is actually not work that has happened within QTI. It's one of the very first results that were published by the high energy physics community some years ago, that investigated the use of a quantum computer to implement quantum associative memory, and that proved or showed the exponential gain that could be obtained for some specific pattern recognition problems in physics by implementing associative memories, rather than in a classical setting using a quantum one. Okay, so this is a kind of one example of how you could expect quantum computers to improve the way we do physics. The other 2 examples are instead results we have produced at CERN. The middle one shows you an example of how we could see improved resource efficiency. This is, I will tell you more about this actually both these results in a couple of slides, but they are here really just to show you. So resource efficiency in a case of quantum reinforcement learning, and improved discovery capability in a case of quantum anomaly detection. You can see in both cases, actually, we'll get back to it, but the difference between the performance of the quantum algorithms, which are highlighted here with respect to basically the other points you see in the plot, which represent the classical algorithms, is always very important. So let me give you a little bit more of information about these 2 examples from QTI. And the first one is really about the anomaly detection. The importance of the role of anomaly detection algorithms is something that has become more and more evident through the years within the community. The bottom line is that we have a very, very precise and very, I would say, well-established description of, of the universe that is given by the standard model of particle physics. This is a theory that has been proved and validated numerous times. It is, however, a theory that can explain only a small fraction of the universe, and we do not have a conclusive explanation on what all of the rest is. And probably, if I mention dark matter, dark energy, these are words that resonate with you. The standard model of particle physics does not explain dark matter at the moment. Okay, so looking for what dark matter is together with other phenomena is really something that is at the core of research today. And it is something that can be phrased as a problem of anomaly detection in a very efficient way. If we do that, it means that the only knowledge that we need to rely on is what we already know very well, which is the standard model. And we don't need to make any hypothesis on what this unknown physics would be. Now, if we set up the problem in this way, we can develop algorithms that can be trained on standard model data. And so I'm talking about AI, machine learning, and deep learning algorithms that are data-driven, that can rely only on standard model data that we know very, very well, and can be trained to flag and highlight any possible hint of new physics as an anomaly. So this is a technique that has been that is being used by the Large Hadron Collider experiment, CMS, Atlas. I didn't explicitly mention their names, but you can find a lot of information on those over the years. And what we worked on was setting up an hybrid algorithms based on a quantum support vector machine for anomaly detections. And what we found out is that building these quantum machine learning algorithms out of, for example, 24 qubits setup on would allow us to find a solution that would be 14 times better with respect to the classical one. And what's interesting about these results, if you look through the details, is that this behavior, this performance is driven by the quantum features, let's say the quantumness of our algorithm. And it's the fact that we introduced quantum entanglement between the qubits. If we do not do that, then the quantum support vector machine does not perform better than the classic one. This is the difference that you see in this plot between the first basically point and all of the other measurements. As soon as we start to introduce entanglement, then we can do much better. It's an example of a result that for me is really important. It shows on the one hand that we can understand very well the quantum the behavior of quantum systems, and also that quantum properties is really at the core of the performance. Another example is the other. I want to give you a little bit more details of the other examples of quantum reinforcement learning I mentioned before, and this is basically an application of a quantum annealer to training intelligent agents. This was done in the context of the AWAKE experiment, which is an experimental facility, accelerator facility at CERN. So what is the background or the context for this? Driving particles or beams of particles through an accelerator is, as you can imagine, a very complex task. It's a multidimensional optimization problems. You would have particles whose trajectory is optimized, squeezed, or let's say, so particles that are aligned on a specific trajectory thanks to a certain number of magnets, and every once in a while their position is monitored and read out in order to make sure that the beam of particle is really along the trajectory that is needed, that is expected. Okay, so this is a problem that can be solved using reinforcement learning technique. And indeed, the accelerators physics community has been looking into classical reinforcement learning for some time for improving the operations of accelerators. So we decided to set up an experiment in which we would try to replace a classical reinforcement learning agent with a hybrid setting in which a quantum annealer can be used to train a classical agent. And in doing so, we found out that we could train this agent much more efficiently. What you see here is basically a plot showing you how large this reinforcement learning setup is in terms of weight. So basically, in terms of the complexity of the trainable system, versus the number of steps that are needed to reach optimality. And if you see those are log scales, you will find that the quantum implementation is orders of magnitude smaller and trains orders of magnitude faster than the classical implementation. There are a number of classical implementation. Each one of these curves and points up here represents a different classical experiment that we've done for comparison. So this is a very, very encouraging result. And in particular, I would like to stress a very important point. In a setup such as this, a quantum annealer can be used to train an agent that indeed it's classical, can run in a GPU, and can run in our experimental facilities without problem. So let me give you now an example of the other directions of our interest and research. So an example of how one of the CERN technologies that's developed in particular for our accelerator setup can be used in the context of quantum technology. And I will use the example of quantum networks and communications for this. But before going there, I just would like to stress one point. Why are we interested in quantum networks and communication? You saw, probably you glimpsed or understood at some point, ours is a distributed community. The World Wide Web was invented at CERN. I don't want to go back to so many years, but even the LHC, the Large Hadron Collider computing grid, is a distributed infrastructure that is used by hundreds of institutes worldwide. So the idea of studying distributed network infrastructure for future computing and future computing solutions for our experiments is part of what we do, of our mandate. And this is the reason why we are interested in quantum communications as the next step. So we want to contribute to the implementation of the novel protocols and be part of the infrastructure that is being created at a broader scale, in particular within CERN member states in Europe. So the example technologies I wanted to focus on is the White Rabbit technology. This is a protocol that has been developed to ensure time synchronization across the accelerators infrastructure at CERN. So I talked about the Large Hadron Collider as a 27-kilometer ring. You can imagine that all of the different components, magnet, operation, monitoring, but hundreds more actually, need to have a very, very tight and precise synchronization. And so it's been many, many years that the White Rabbit technologies has been developed. It ensures sub-nanosecond accuracy and a precision of the level of a picosecond, actually, and has been tested at the scale of few tens of kilometers at CERN. It has now turned into a fully open source and commercially available technology, which has also been recognized as a standard at the level of IEEE recently. CERN has also launched a collaboration dedicated to White Rabbit. This happened last year. You can see actually in this picture the initial number of the logos for the initial members that participated in the creation of the collaborations. There's many more now. This is the updated list of members that contribute to White Rabbit. And so for us, beyond QTI, because White Rabbit is a technology that has existed at CERN long before the Quantum Technology Initiative existed, but it's a very, very nice example of how work had happened at CERN and that was specific to our accelerator network development is now being studied for many different applications, and in the context of QTI, also quantum technologies. So I'll give you an example. One is the collaboration we have set up with New Quantum, and this is really about trying to use the White Rabbit timing technologies for data center enabled through quantum communication networks, so distributed quantum computing, basically. Another very, very nice example I wanted to give you is a recent experiment. This is still ongoing, which tries to use White Rabbit beyond the problem of time synchronization, and it's the idea of using White Rabbit on deployed fibers in order to minimize the downtime of the network. So the problem so this is basically it's actually a complex problem. It's the idea of compensating the behavior of the network in order to ensure high fidelities and at all time, while at the same time reduce the network downtime the maximum that we can. So of course this is a matter of compromise, and the experiment is set up in such a way that basically just use the synchronization step when it's needed. When you highlight and you monitor and you see that there is the need for a compensation, it's the only time when this happens. So it's a very nice example that QTI is running together with Connect and Deutsche Telekom. In fact, the experiment is set up in the Quantum Labs in Berlin. And the idea is really to continue monitoring link delays and trigger the compensation signals only when needed. I'll just show you a few pictures to conclude. It's always nice. You can see our researcher, Anik, that is in the Quantum Lab and is having pretty good time, I would say, in running this experiment. So data taking is ongoing. To conclude, I just wanted to stress again the role of collaboration and how important it is for us to work with a broader set of partners. The quantum ecosystems is a complex ecosystem, and CERN wants to participate to it in the most flexible way. In this sense, I want to give you two examples of the important role or the way CERN is trying to approach this aspect. The knowledge transfer group, of course, is essential. Their role is really to try and set up opportunities for innovation together with external partners and extend and increase impact at the broadest possible level. And there's also the specific case of the Open Quantum Institute, which is coordinated by CERN, and it's really meant to facilitate collaboration between different stakeholders at the worldwide level. This is specific to quantum computing and their impact and their societal impact, in particular for everything that is related to sustainable development goals. And in order to achieve this, we have also created a collaboration framework for the Quantum Technology Initiative. This is something that at CERN, it's a very important tool at CERN that allows us to build collaboration of different kinds with other labs, with other institutes, universities, but also with important actors in the private sector, in a way that is as flexible as possible. So there are multiple approaches that can be covered by this, by the agreement, the framework we have within our hub. And I think it's a very nice example of the efforts we are taking or we are making towards working with a broader set of partners as possible. So let me go back to the lessons learned. I will not go through them again. I hope you remember my first slides and that they became clear through my talk. I just want to conclude with a little bit of an outlook of what the future means for us. What the community is discussing at this time is projects like the Future Circular Collider. This is, if approved, is one of the will be a huge, I would say. I talked about the Large Hadron Collider as a 27 circumference, 27-kilometer ring. This would be around 90 kilometers long. So you can imagine the scale. Why do I mention it here? If a project like the Future Circular Collider is approved, will not start operations before the mid-40s, possibly later. It will run till the end of the century. This is a time scale that really, allows us plenty of time to study quantum technologies and quantum computing in particular in, in a completely synchronized way, if you allow me. So with this, I conclude. Well, thank you for your patience.
Okay, thank you so much. So, oh, really impressive what you are currently doing and the future. So I hope that to be invited to this new project and to travel inside the project, because this if it's as big as you have shown in the picture, it's gonna be really big. So let's go now to the cool part, the question, the part that I really like, because I have the chance to ask questions. Hopefully, not so difficult, so so you can answer to all of them. But before jumping to the first question that I have here prepared, you were talking about picoseconds. So I want just to give like a visual representation of how fast is a picosecond. So if you stretch 1 second, if you stretch 1 second, it will be around 31,700 years. So a picosecond will be a second to that
Yeah.
31,700 years. So that's a really like visual representation that got me astonished the first time I heard about that. So yeah, that's
It's really good that, yeah, thanks for doing that, because it is true that sometimes we talk this way and
yeah.
people can't really appreciate, because if you say it as you just described, it's impressive. It blows my mind too.
Yeah. So yeah, we were talking about picosecond. Like we know it's fast, but how
Yeah.
fast it is? Like it's really fast. Okay, so let's jump to the first question. And as we are a consortium about industry, and we are in this realm where there are like a lot of companies and different initiatives, the first question that comes to my mind is what motivated CERN to launch the Quantum Technology Initiative, and how it has been evolving since the launch till now.
So this was really because of, as an answer to as interest that we saw rising in the community. It was clear. So the initiative was launched in 2020. It required a couple of years preparation. It started in 2018 with a workshop that we had organized to probe the level of interest in the high energy physics community concerning these technologies, because we understood at that time that this would be a very important, that this was already, right, at the time, an important topic that would develop very fast. So we wanted to be prepared. On the one hand, it's clear that the community at the time was really curious and interested in these technologies in general. So I'm talking about computing, I'm talking about
Yeah.
sensing. Yeah, but it's also research and technologies that require a long time for the integration in our way of doing things, right? So if we want to introduce the case of quantum computers, it's really a good one. If we want to introduce quantum computers in our way of solving or doing data processing, we need to understand how to write algorithms. We need to even reshape or change the way we think about problems. Okay, it's not even just a matter of technology. It's even so. This is really years. It requires years.
Yeah.
So the Quantum Technology Initiative was launched as an exploratory initiative. At the beginning, we were really trying to survey as many use cases and possible and applications as possible. And we started to have a very good feeling of where those technologies could be more important. So or more useful for us.
Yeah.
So starting from 2024, we started what we call phase 2 of the Quantum Technology Initiative that became much more focused on a certain number of problems that we understood could be more relevant for us. So this was also the evolution.
And when you're talking about relevant for you, is relevant for CERN itself, for the scientific part, for the, I don't know, the use case or industrialization part. And the second question that I have is how you collaborate with these external partners in quantum technology, like developers, startups. So a little bit of both.
Okay, so yeah, so there are slightly, I mean, there are little differences depending on the exact topic we are discussing. So that's why I always stress we try to be as broad and flexible as possible. For example, when I say relevant for us, I mean useful for research. And this can be at the level of managing infrastructure. And the example of the quantum reinforcement learning is a way of improving optimization of the accelerators infrastructure, but also improving, for example, the computing models, solving some of the problems we have in the data processing, or designing better detectors for specific physics problems if you're thinking about quantum sensing, which I really didn't describe in the talk, but it's a very important area of research for us as well. So usefulness for us is really at this stage the possibility of solving certain number of problems in a way that can be more efficient, more energy efficient, or maybe can give us a better reach in some physics searches. And so from the point of view of the collaboration, this really translates into, with different partners, with industry or other labs, this really translates into project-based collaboration. When we see that there is a match between the kind of problem we want to solve and the expertise, it can be, for example, expertise that we have at CERN that can be used, for example, for improving specific problems that have a much broader reach. And the new quantum example, I think it's a good example. So where Trabit used in distributed quantum systems, distributed quantum computing systems is an example. But in other cases, we can have also joint PhD students in which students from different institutes which have a more of a quantum information background come to work at CERN and bring their institute expertise so that we can work together towards defining new quantum algorithms for our problem. So this is another example. So it's two very different ways. There is a little bit of everything.
Yeah, and talking about the industry and the companies, how do you balance or you keep balancing the partnerships or the project that you are talking about with the CERN's open science principle? So there is like this duality about making projects for companies or with companies and having the open science.
Yeah, so well, obviously, open science is a core is part of the core. It's a core principle at CERN. It's part of what we do, and it applies to everything. But that said, we've always this is really mostly thanks to my colleagues that really drive the collaboration, in particular with industry, and so also the knowledge transfer department. They're great of managing and finding the best way to manage this. But the idea is that what would typically happen in a general collaborative project would be that there will be some part of the technology that is naturally open that can then become or further leveraged by a company for their own either product or for bringing the technology at higher readiness level until they can become products. So there are, again, depends on the technologies, but we can have both. The two systems can coexist.
Okay, now talking about the technology and getting into that, I'm gonna ask. Maybe it's personal, but in general, how do you see the integration of these quantum technologies within the high energy physics models that you already have? That's one question. And the other that maybe is more subjective. What do you think that is the most promising or quantum algorithm or technology or application within this high energy physics, or in general, if you feel like?
Okay, so again, for as far as the integration is concerned, I would say again, it really depends on what we're talking about. For quantum sensing, that is more straightforward in the sense that quantum sensing based detector could become just different kinds of detectors that are used together with the others and probably wouldn't require too much adjustment. So there are already some experiments that are being planned with what we could categorize as loose way quantum sensors. So from that point of view, the integration is in some sense easier. In the case of quantum computing, and this is actually the reason why we are so much focusing now at this, really on this, there are a lot of different challenges that need to be addressed. In general terms, what we, as many other users, so I look at ourselves from the user's perspective, and now if we start looking at quantum computers as just another kind of accelerator, or that hardware accelerator that can be integrated in a broader classical setup, then once we have identified the specific kind of problems that we want to run on a quantum computer, then the change of paradigm becomes just, and I'm saying quote unquote, because just is not the right word possibly, but it's really about extending our infrastructure to a more heterogeneous setup. So in the same way we would introduce GPUs and other, which are not that common right now in our own internal infrastructure, but let's say the same way we extend to a more heterogeneous world, we would do that with the quantum computers as well. Once, obviously, the technological engineering, but also algorithmic challenges are faced. And as far as the most promising applications, I will give you the more institutional one and my personal one. So if I try to be more realistic, I would say that long term, so fault tolerant quantum using quantum computers as simulators for simulating physics processes is one of the most promising applications. But I'm interested in quantum machine learning, possibly because of my background in classical machine learning. I think this is also a very, very promising field for many reasons, because if you can prove that you can accelerate the train, or that can improve trainable systems on a quantum computer, then those become tools that can be used on a broad range of problems. They are very, very interesting algorithms to study today, because the behavior of trainable systems, once they are implemented on a quantum computer, changes slightly. So there are a lot of interesting things that we need to understand in how fast we can train them, how well they can generalize, and things like that. So it's a very interesting field. The disadvantage and the limitation for running those today is that typically trainable systems require a lot of iterations, and in particular a lot of iteration between the quantum system and the classical one. And at the moment, this is a bottleneck. So
I cannot agree more. Like I'm also really excited about QML. It's a field that I really like, and I would like to know more. And also, I guess that from CERN, and don't take my words like that. So it's easy to apply quantum technologies because you have quantum data. Like all the physics that you are doing is easier for you to work with in the sensing part, because you have this kind of data, and also in the computing, because you have in some way encoded this kind of data. So yeah.
Yes, we should not. So yes, we should not forget though that if we are talking about simulation, for sure. So using a quantum computer to simulate quantum mechanics, quantum field theory, it's really, it's what you could expect to be the default application.
Approach, yeah.
Yes, approach. From the point of view of data processing, it's more complicated, because our data is actually, it's quantum in nature, but it's classical because it's the outcome of measurements that happen, of our detectors.
Yeah.
So From that point of view, yes, we are trying to reconstruct quantum behavior for classical data. And so we do expect quantum computers and quantum algorithms to work better, but the connection is a little bit looser, I would say, more
Yeah.
fainter than
Yeah.
with this tech.
I guess that in the future we could integrate that directly. Not right now, but I hope that one day we can do so.
And that would be the very, very nice step. So the integration between quantum sensing and thinking about quantum computing as as a sort of a real-time processing, that like in-sensor computing would be really the next
Yeah.
step.
Totally, totally. Well, one last question before we close, and we have talked about the computing, the physics, the ecosystem in general, but I haven't asked you about the communication part. And I would like to know, as you were talking about this network and everything, how the Quantum Technology Initiative will work with the quantum network in integration with the broader European initiatives of quantum communications? Like, are you currently working with them? Do you plan to like
Yes.
talk a little bit about that?
So yes, so there are a few things that are ongoing. We are discussing with the local actors in the area, in the Geneva area. I cannot be very precise actually because we need to
Okay,
wait.
okay.
Yes, for the official announcement. But we are very well. Let me say this: we are very well integrated with the local community. I'm very proud to be part of an effort, and it's ongoing within Geneva. We are connected to the French Refimet network, which brings high frequency, the high precision frequency distribution to CERN, and we redistribute that within CERN through a certain number of experiments that can run their tests and compare the signal that is distributed to their own atomic clocks that they use for their experiments. This happens in particular in the context of the what's called at CERN the antimatter facility or set of experiments. But more broadly, CERN has been a long-term partners of broad collaboration like the GEONT. This is at the level of the general European networking infrastructure, and so obviously everything that's related to quantum falls also into that category. So there are a few examples. This is really it's actually a good example of the way we want to be integrated with the activities that are happening at the European level.
Yeah, that's great. It's super good to hear that, and I hope you haven't said anything compromising because,
I hope so too.
as you know, this is gonna be forever in YouTube in one of the YouTube
Exactly.
servers. So, okay, so thank you so much. Thank you so much for your presentation, for being here, for this nice talk and solving some questions. This is gonna be in YouTube, as I said. So if people have questions, they can like post them and we can like get them to you or try to answer them in the nicest way that we want.
Well,
So
thank you.
again, thank you, and thank you also to people who is watching this video. Just a final remark that really helps us. Follow us on LinkedIn, like the video, subscribe to our channel, share this video, because this is the way that we can grow this and bring more people, more interesting people like Sofia. So again, thank you all, and bye.
Bye.